Today we're going to be talking about the nature of waves. So the first thing we need to understand, what is a wave? A wave is a repeating disturbance that transfers energy through matter or space. We're going to find out there's a couple different kinds of waves and all that kind of stuff, but just remember it is a repeating disturbance that transmits energy. So wait a minute, what does transferring energy mean? Well, what we mean by this is when objects with kinetic energy contact molecules, some of that energy is transferred into the molecules. This causes the molecules to move, which passes energy from molecule to molecule. When we stop and think about how your voice or even water in the ripples of a pond move, you toss that rock out there, the rock hits the water, causes some energy of the kinetic energy of the rock to be then transferred into the water. And that energy then moves out away from the impact in the rings that happen. And if you watch and have a still enough pond, you can actually make the ripples travel the entire circumference of the pond. If you throw it right out in the middle, you can watch the ripples happen. And that's what is happening. You're transferring the energy from the throwing rock, the kinetic rock, into the water, and then the water is now distributing that energy out because it's still there. Waves also carry energy without transporting matter from place to place. And this animation is really cool because what it shows is that even though energy has been transmitted from, say, the left to the right as we watch our waves move through, we can actually see that the molecule itself, even though it moves, it tends to come back to the relatively same location. The more energy they have, the farther they'll move. If you go down here farther deeper down where their water waves aren't being affected, aren't affecting the water, you'll see the molecule moves very, very little. And if you get down deeper, less and less, which makes sense if you've ever been out on a swimming on a really choppy, windy, wavy day, especially out in the ocean. If you dive down, you don't feel the waves moving nearly as much when you're down under the water, swimming under the water. But as soon as you get to the top, you feel that wave moving you back and forth, but it doesn't carry you anywhere unless you're actually riding the wave. And then you're basically falling, using gravity to follow you as you fall, you the gravity to pull you down as the wave is actually pushing you back up. So that's what surfing is. Wave riding, it's a lot of fun if you've never done it. So we can see here they carry the energy, but they don't move the matter. They don't transport the matter from place to place. The matter tends to stay in roughly the same direction. Waves only travel as long as they have the energy to carry them. So you think about that rock. When you throw that rock out into the pond, if it's a small rock or doesn't have a lot of energy, the waves tend to die out really quickly. But then you chuck a really big rock out there, well, the waves will move a very long way. Okay? So same thing, we think back at the illustration we just saw. As the wave was moving, some of the energy was lost to the surrounding molecules. And so that's why you don't have the same amount of energy that you cause when you first make a splash to the other one because energy is lost to the surroundings. How do you produce waves? Waves are produced by vibrations or rhythmic motions. And if you've ever done the ropes training or something along those lines, you know that you're making a wave because you're doing a repeated pattern over and over again. And that's the rhythmic motion. And so if you've ever done this, it's a really great workout. Mechanical waves. So talk about different kinds of waves here. Medium, first off, we need to talk about is what the wave travels through. There are different kinds of medium. There's water, there's air, there are rocks. Certain waves travel better through different medium, and we're going to talk about that. A mechanical wave is a wave that can only travel through matter. Mechanical waves, therefore, wouldn't work in space. Okay, we'll talk about can someone hear you screaming in space. Mechanical waves are waves, again, that can only travel through matter. There are two different kinds of mechanical waves. The first type of wave we call a transverse wave. Think of the wave in the water going up and down. The ropes, as you're moving the ropes up and down, this is a transverse wave. The rhythmic pattern is up and down. Okay? Then there is a longitudinal wave. A longitudinal wave, it's compressions and refractions. It's squeezing together and moving apart. And so we can see that rather than moving up and down, the rhythmic motion is back and forth. Okay, and those are the two differences between the two types of mechanical waves. Remember, these are waves that only travel through matter. Okay? Sound waves are longitudinal waves. There are air molecules that are being compressed, and as the sound moves through the medium of the air, that sound is carried. Okay, so demonstration here. Seismic waves, however, if we're looking at earthquakes, they are both transverse and longitudinal. And you can see down here by these graphic illustrations that the S wave, or the transverse wave, right, travels up and down. See the block move. Whereas over here with our P wave, or our longitudinal wave, it is the compression, just like the sound wave, so it moves back and forth. Now you can think about a building that's being subjected to a back and forth motion as well as an up and down motion, and that is why earthquakes are so very destructive, because it combines the back and forth and the up and down, and a lot of structures aren't able to take that type of motion. There are different parts of the transverse waves we need to talk about, because this will lead into how we measure the wavelength, frequency, all that kind of stuff. So, and you may have had some of this stuff in middle school, but we're going to refresh it here. So the parts of a transverse wave, first off, we have crests. Crests are the high points. Troughs are the low points. We have a crest and a trough. And the longitudinal wave has the same concept, but we don't call them crests and troughs. We call them compressions and rarefactions. Okay, they're the same thing, but because a transverse wave goes up and down and a longitudinal wave goes back and forth, we use different words to make sure we differentiate. We should know the differences between the two. So a transverse wave, don't get tricked on this on the quiz, transverse waves have crests and troughs, and longitudinal waves have compressions and rarefactions. Other properties, we have wavelength. This is the distance between one point on a wave and the nearest point just like it. So crest to crest, trough to trough, or midway to midway. Frequency is the number of wavelengths that pass a fixed point in 1 second. Okay, so how many wavelengths are moving point past this point in 1 second? That's frequency. The period is the amount of time it takes one wavelength to pass a point. So as frequency increases, so the more wavelengths you have past that fixed point, your period decreases. Because remember, the period is for just one wavelength. So more frequency, you have more wavelengths passing through, which means our period gets shorter. Okay. Amplitude, a measure of the size of the disturbance of the wave, how far up and down you're going in a transverse wave, or how far back and forth you're moving in a longitudinal wave. That is amplitude. Here's a diagram that shows those things. If we have time of 1 second, notice we have 1.5 wavelengths. Notice the period wavelength is from same to same. Down here, same to same. And so if we look at this, we see we have an up, right? And there's one, actually we have two waves. I apologize, not 1.5. And then there's another wave. So we have frequency of two wavelengths have passed in that one side. The period it takes for one of these wavelengths to go through would be half of a second, okay, or a third of a second actually, because we have 3 wavelengths. We have in 1 second, so it would be 1/3 of a second. All right. Calculating wave speed. How do we calculate a wave speed? The wave speed is depends on the medium in which it travels. Some things, sound waves, travel very well through air. Do they travel through solids? We might have to do a lab to figure that out. So depending on the medium will depend on the speed of the wave. We'll find that especially with light. Light is a wave, and that will change depending on what it travels through, which causes some really cool optical illusions. But wave speed, frequency, and wavelength, they're all related. And how do we know they're related? Well, because we have an equation mathematically that shows us that. It says wave speed is related to the product of the wavelength times the frequency. So it's the product of wavelength and frequency. So if we multiply our wavelength, which we use as a symbol of lambda, it's the Greek symbol. It looks like a wave, which is why they picked it, but it's the Greek symbol and it's called lambda. So it's V equals lambda times frequency. So here's a question. The wavelength of a wave that is traveling at 343 meters per second, well, that's obviously speed, and has a frequency of 440 hertz. Well, to do that, we would just divide both sides by f. So the velocity, or the wave speed, 343 divided by The frequency, which is 440 hertz, would then give us a wavelength of 0.78 meters.